or accept our invitation. Thank you, sir.
Okay. Thanks a lot for a nice introduction. I'm also thankful to Akbari sir, who has invited me, and I'm also thankful to principal who has started and initiated this kind of certificate courses, which is also industry based. So I'm very much happy to see that like any pharmacy colleges is running industry oriented certificate courses. So it is very good part of this college. And I'm also congratulations to receive NBA accreditations recently to all faculty members and all this.
Thank you,
And
sir.
I'm, yes, and I'm also thank you all students and congratulate students that who have enrolled in this unique certificate courses, and they are also keen that they are willing to learn something new which is out of syllabus. Okay. So with this, I will start my presentations. So I'm just closing my video and I'm sharing my presentations. So my screen is visible.
Yes, sir. Yes, sir.
Okay. So I hope that everyone has some brief idea about the HPLC, and this session is going to be a very basic lecture. Okay, so that's why I have named that lecture that ABCD of HPLC. Okay, so means you need to learn the whenever you start with any chromatographic technique, you should learn the what are the basics, what are the basic terminology that is required. Okay, so if you read any book, if you read any book, any article, any chapter, and in that there are so many scientific terminology which is out of any box. Okay, so when you read these chapters, books, or articles, at that time, if you know the basic meaning of this terminology, then it will be very helpful for you to read the articles or read the chapters. Okay, so to gain the basic knowledge, to gain the basic concept about the what is the meaning of a particular term, so that will be covered in today's lecture. Okay, so like ABCD, we have many alphabeticals in our English alphabetics. Okay, like HPLC have a means any chromatograph. These chromatographic techniques have a many alphabetics or many scientific terms it has. Okay, suppose basic terms and concept, we frequently hear the name like peak height, peak width, retention time, adjusted retention time, chromatogram. Okay, so what is this? What is the meaning of this? So we need to learn all those things because these terms are frequently used in the these techniques. Okay, so we need to go one by one. Okay, so first of all, the retention time. So the time between the means first of all these are the chromatographic techniques. So chromatography techniques. If I ask to what is the chromatography, then that meaning is a separation technique. Okay, so separation technique means once we inject the sample which has a mixture of one or more compound, once it goes to the chromatograph itself have a two kind of system. One is a stationary phase, another is a mobile phase. Okay, stationary phase is stagnant and mobile phase is moving around the stationary phase. Mobile phase may be a liquid, maybe a gas. Okay, when it is a gas, it is called as a gas chromatography. When it is a mobile phase is a liquid, then it is called as a liquid chromatography. Okay, sometimes chromatography also classified based on the stationary phase. Like if you are using the column kind of stationary phase, then it is called as a column chromatography. Sometimes we have used the planar, means TLC plate, then we can call as a planar chromatography. So based on the mobile phase and stationary phase, there are 2 to 3 types of classification system in chromatography. First one is depends on mobile phase. That is example is gas chromatography or liquid chromatography. Second is by stationary phase. So in stationary phase, planar chromatography, column chromatography, affinity chromatography, ion exchange chromatography, chiral chromatography. So all these examples are the based on the stationary phase. When it comes to the principle of separation. Okay, principle of separation, then it is a again different techniques are classified. So all techniques can be classified in different way. You need to define that, means you need to remember easily when you have some understanding, basic understanding, that why this chromatographic technique is classified on which basis. Okay, but in any technique, the uh, retention times remain same. The meaning of retention time, it remains same. Means, what is the meaning? The time between the sample injection and the peak maximum is called the retention time. You can note down. I request all students to note down each and every one terminology, because uh, at the end of presentation you need to know that uh, how many terminologies or terms we have gone through. Okay, so rather than just sitting, I can request to all students that write down the just name of the terms. So at the end you will know that how many terms we have completed. Okay, so retention time, it is denoted as a TR. The time between the sample injection and peak maximum is called the retention time. Okay, and the retention time of unretained component or the first baseline disturbance by the sample solvent is called the void time or hold up time. Okay, so if you look at the first paragraph, first figure, so the retention time, that is TR. So sample injection in this is a chromatograph. Okay, chromatograph. It is a chromatograph. So the 0 minute, it means the sample is injected, and third, and that peak maximum, it is at certain 1.6 minute. That is a retention time. So it is called as a retention time. So sample injection to peak maximum.
Sorry
What
to
is
disturb you, sir, but your screen is not moved, sir.
okay? 1 minute. Right now,
Yes, sir. Now it done. Yes, yes.
yes. Sorry to this kind of
No problem. No problem. No problem, sir.
okay. So the basic terms I have just requested to students that you can note down. So this is the basic chromatogram or chromatograph. Okay, where it is a common picture in any chromatography, that what is the output of the any chromatographic technique. This is the output of any chromatographic technique, and that output is called as a chromatograph. Okay, so time between the sample injections to peak maximum, it is called retention time, and this peak is looks like this, and the first disturbance 8.34 minute, it is the unretained sample. We can call by define, it is called as a TM, the retention time of an unretained component or the first baseline disturbance by the sample solvent is called the void time or hold up time. Okay, so TM is the total time spent by any component in the mobile phase, and the adjusted retention time is equal to TR minus TM. So whatever the retention time is total minus TM means that is the hold up time. It is called the time or solute reside in stationary phase. So there are two things. Does analyte reside in stationary phase or analyte reside in mobile phase? So there are two things. So before the adjusted retention time, the solutes resides in the stationary phase, and before the hold up time or before the void time, the analyte is in the mobile phase. Okay, so by definitions, uh, and this is the peak shape. Okay, so this is the peak shape, means the ideal peak shape, and here there is a written that for Gaussian peak. So Gaussian, what is the meaning of Gaussian peak? So it is called as a ideal peak. Okay, so whenever you find the Gaussian term, what is the meaning of Gaussian peaks? Okay, so Gaussian peaks, it means that the ideal peak. If you divide your peak from the peak to the center. Okay, so it will convert into the two equal part. Okay, if you divide your peak from the middle, the part A it is in left side, part B it is in right side. If A divided by B is equal to 1, it means that both parts are equal. Then and then it is called as a Gaussian peak. And every chromatographer have a aim to achieve a Gaussian peak. Means ke we cannot means we have always trying to achieve the Gaussian peak shape. Okay, means ke more peak means ke more sharper peak. Okay. So any kind of response is not acceptable. Only Gaussian peak kind of peak shape, means the ideal peak shape, is acceptable for the chromatographic conditions. Okay. So here there are so many terms again. What is the WB at the end in chromatogram? At the end it is written WB. So it is meaning that peak width at base. W means width and B means base. Okay. So peak width at base, it is called as a WB. H is equal to called as a peak height. Okay. So these are all are the terminology we can call as ABCD. That one is a retention time, another is a hold up time, third one is a peak height, fourth one is a peak width at base, and sixth one is a peak width at half height. The 1 by 2 is W 1 by 2 is peak width at half height. It is just named like this. Okay, and it is called as a peak half height. Okay, why these all terminologies are required? Because in many different books, different terminologies there. Here it is written that for Gaussian peaks, width at half height means W1 by 2 is equal to 2.355 into sigma, and peak width is equal to WB is equal to 4 into sigma. It is particularly important, and I will highlight this point in next slides. Means so these are very much important. Why W1 by 2 is there? Because in USP is generally not measuring the peak width at base, while the other pharmacopoeia and other standards are measuring the peak width at the base. But USP is not measuring the peak width at base. They are measuring, they have said that you have to measure the peak width at the half height, because you will get the more information or more precise information at the middle of the peak. So that's why the two concept is there: peak width at half height, and another concept is peak width at base. Okay, and the solute peak has both a peak width and peak half height. Okay, peak height. The peak width is usually measured at the base. That is so we have already covered this part. The peak width is usually measured at the base WB, or at the peak half height, that is W1 by 2, and the peak area. So right now software is there to calculate the peak area. Okay, but to so that's why it is more important, because in chromatography quantitation is done on the peak area or peak height. So peak area is very much important, and how to calculate the peak area, that is a different thing. If it is from USP side, if you are using the USP peak area, then the area is considered, peak width is considered at the half height. Otherwise it is considered at the base. Okay, so how to calculate the peak area? Okay, is roughly equal to 1 by 2 into peak width at base into height. Okay, so peak width into height, it will give the peak area. Okay, and here said that for Gaussian peaks, Gaussian peak means again it's ideal peak. WB is approximately equal to 4 times. WB is equal to 4 times the standard deviation for S, which brackets 95% of the total peak area. So why standard deviation 4 times is there? Because it will almost cover 95% of the peak area. The height or the area of peak. So you should know, you should learn about this concept, like Lambert's-Beer's law. What Lambert's-Beer's law says: the concentrations or absorbance is directly proportional to the concentration. Means you increase the concentrations, then the peak area or absorbance is increased, or increasing in the absorbance indicates the higher amount of concentration. So likewise, in HPLC also, or any chromatographic also, peak height or area indicates the amount of analyte component. Means peak area is more or peak height is more, then you can say that there is a concentration is in more amount. If peak area or peak height is too small, then you can say the amount of sample is too low. Okay, and this, as I said, the peak area is commonly used to perform quantitative calculation. So after getting this few terms, means again I am repeating what terminology we have gone through: retention time, adjusted retention time, peak height, peak width at base, and peak width at the half height. Okay, and Gaussian peak, the meaning of Gaussian peak, and what is the relevance of Gaussian peak into the peak area. Okay, so that terminology we have gone through. Now the term is retention volume, void volume, and peak volume. Okay, you need to uh, get this terminology. Okay, so retention volume is the volume of mobile phase needed to elute the analyte at given flow rate. Okay, so it is just basic terms that how much amount of mobile phase you require to elute the particular peak. So flow rate. Now again, one term is flow rate. So what is the flow rate? Okay, the mobile phase are flowing at a particular rate. It is called as a flow rate. Okay, so here retention volume, it means VR. V means volume, R means retention. So VR is equal to TR into F. F means flow rate, and TR means we have already learned that TR is retention time. Okay, so suppose if my retention time of peak is 7 minutes, if my retention time of my peak is 7 minutes, and I am using the mobile phase flow rate at 1 ml per minute, okay, at a flow rate of 1 ml per minute, retention time is 7. So what is my retention volume? If I ask questions right now to students, okay, so if it is allowed, then can anyone give me the answer? That what is the retention volume in terms of TR into F? If my retention time is 7 and flow rate is 1 ml per minute, then what is my flow retention volume? Can I ask questions to audience? Can anybody can answer the questions? Okay, I think it is a 2 hours lecture, so might be students are, so if it is not interactive, then we lose the momentum. Okay, so I request students to be interactive, so that these 2 hours will be utilized more, because unless you don't understand the basics, okay, you will find the difficulties in the higher technical lectures. Okay, so retention volume, if my retention time is 7 and flow rate is 1 minute, so 7 into 1, so it will give the 7 ml. So just 7 ml is required for the retention volume of my peak. Similarly, void volume. The void volume VM is the total volume of the liquid mobile phase contained in the column, also called a Holder volume. It is the volume of empty column minus the volume of the solid packing. Note that Vm is the sum of intraparticle volume V0 and interstitial volume Vc inside the pores of the solid support. For most columns, the void volume can be estimated by equation number 3. So, what is the column volume? So, to measure the column volume, okay, there is a equations, and this equation is 0.65 into Vc, VC means volume, column volume of column, is equal to, again we simplify the equation of 0.65 to VC. Okay, it is equation is 0.65 pi r square into m. So where r is the inner radius of the column, L is the length of the column, Vm can also be estimated from Tm in the chromatogram, like Vm is equal to Tm into flow rate. Okay, and the peak volume, also called the bandwidth, is the volume of mobile phase containing the eluted peak. So peak volume generally called as a Wb into flow rate. So if you understand the concept of flow rate into means, if you understand the concept of flow rate and volume, then you can define how much volume is required for the each and every term. If it is adjusted retention time, then you need to multiply flow rate with the adjusted retention time. If it's the peak volume, then you need to multiply peak width at base into flow rate, and if it is a retention volume, then you need to multiply flow rate with retention time. Okay? Then retention factor, it is again very much important factor. The retention factor is the degree of retention of the sample component in the column. So, and it is denoted as a small k. Okay, so you need to note this factor, because this factor is quite important, because it is also asked in the some type of questions in Viva questions in the Viva, okay, or in examination or interview, that retention factor K is the degree of retention of the sample component in the column. So what is the retention factor? So K is defined as the time the solute resides in the stationary phase relative to the time it resides in the mobile phase. So it is a ratio. Okay, so it is the ratio of solute residing in stationary phase divided by the solute residing in the mobile phase, and in IUPAC terms was also referred to as a K days or capacity factor in many reference. So retention factor or capacity factor, both are equal in terms. So when you operate the software or when you go through the any book, when it is written that retention factor, so you will easily identify that what is the meaning of that. Okay, so I will also explain by the equations. And the K, what is the importance of K value, means what is the importance of retention factor. Okay, so it is an important factor, to defining the retention of the analyte. Okay, so desirable K values for isocratic analysis are 1 to 20. Okay, so what is the desirable value? Means the retention factor, we define that it is a ratio of solute residing in the stationary phase and mobile phase. But what is the value of that? Okay, so the value, the meaning of that, it is in between 1 to 20. Okay, so when you are getting this retention factor, your value should be 1 to 20. And equation by if we define by the equations, then K is equal to T dash R or Tm. It is called as a Tr minus Tm upon Tm. So Tr is what? Tr is the retention time, and Tm is what? Means it is an adjusted retention time. So if you look by the example, so everyone should focus on this line, because if you don't get any idea from the definitions, you will get more idea from this slide. Okay, so retention factor K is equal to Tr minus Tm upon Tm. So we know that what is the Tr and Tm. So for our previous example of this, retention time is 1.6 minute. Okay, and so that is the retention time. And okay, so this is the retention time, and this is a Tm, means first baseline disturbance. So it is called as Tm. So if Tm is 0.34 minute and retention time is 1.6 minute, so the retention factor K is equal to 1.67 minus 0.34 divided by again Tm, so that is 0.34. and if you simplify these mathematical equations, then k is equal to 3.9. Okay, so it is in between 1 to 20. Okay, so if you don't understand my definitions, you can easily get the information from the definition. Okay. Similarly, the equations Tr minus Tm means we can get the idea that what is the relation between the uh, retention factor and the, so it indicates that retention time is proportional to the k, means retention time is depend on the retention factor. If retention time is more, then retention factor is also more. Okay, if retention time is shorter, then retention factor is also shorter. Okay, note that multiplying both sides with the flow rate, a similar equation for VR is obtained. Okay, so again, the relation between the retention factor and volume, it is also depends on that. If the retention time is more, then the volume of mobile phase required to elute is also more, and retention factor is also more. Okay, so you will get the information from these equations. So now what is the interpretations when we are getting some value which is in between 1 to 20? Okay, a peak width k is equal to 0 is a component that is unretained by the stationary phase and elute with the solvent front. So peak width k is equal to 0 means if you find the k value, it is 0, then sample is unretained by the stationary phase and elute with the solvent front. So you can call as a there is a no separations in mobile phase is means sample is there is no separation of the compound, and mobile sample is eluted with the mobile phase. Okay, and k, so that is the meaning of k. When the retention factor is 0, then you can conclude like this: when the k is greater than 20, indicates that component is highly retained, and in most analyses, analyte elute with the k between 1 and 20, so that they have sufficient opportunity to interact with the stationary phase, resulting in a differential migration. Okay, so if k is greater than 20, so first case means first case there is a 0, so 0 means there is no separation. If k is greater than 20, then what indicates? It indicates that component is highly retained. Highly retained means the retention time is too longer. Generally, that is not acceptable when retention time is too longer of any analyte. Okay, so analyte elutes with k between 1 to 20. So for that, any chromatographer have a aim to do the to separate the analytes in between 1 to 20, so that they have sufficient opportunity to interact with the stationary phase, resulting in the differential migrations of the mobile phase. So analyte eluting with greater than 20 are difficult to detect due to excessive band broadening. So the k is also optimized, means optimized through your solvent, through your column, and through the mobile phase proposition. Okay, so you can optimize or you can get the appropriate retention factor with the appropriate method condition. Okay. So chromatography is a thermodynamically based method of separation where each component in the sample is distributed between the mobile phase and the stationary phase. So sample is distributed in mobile phase, it is called as a XS, and mobile phase distribution in mobile phase, it is XM. So partition coefficient means it is called as the principle of liquid chromatography, that is a partition coefficient. So partition coefficient means what? It means that the sample is distributed between the mobile phase and the stationary phase. The ratio of it is called as a partition coefficient. Okay, the equations. So in this, where xm and xs are the concentration of analyte x in the mobile phase and stationary phase respectively, the distribution of analyte x is governed by the partition coefficient k. Okay, so the principle of liquid chromatography is also partition coefficient k, and the definition of it is also here the same. and partition coefficient it denoted as a capital K, while in case of retention factor is denoted as a small k. So K, small k can also describe the ratio of total number of moles of analyte in each phase. Okay, so means if we multiply by the moles of stationary phase, moles of X in stationary phase, and moles of X analyte or X in mobile phase, then simply we get the equations like retention factor is equal to capital K means partition coefficient is into volume in the stationary phase and volume in a mobile phase. Okay. So K, how we can control the retention factor? Okay, as I say, the strength of the mobile phase, the nature of stationary phase, and a temperature at which the separation is performed, by which we can means what indicates. See, these are the basics. So if you don't get the retention time, appropriate retention time, so what is your next trial? So it is not only a trial and error based approach. It is generally scientific evidence or scientific on the scientific ground. You should design the some scientific trials, technical trials. Okay, when you are not getting the appropriate retention time in HPLC. So in this, wait a minute. So the strength of the mobile phase, the nature of stationary phase, and the temperature means if you are not getting the retention factor, then you can have an option to optimize your mobile phase. You can change your stationary phase, or even you can update your temperature requirement to do the analysis. Okay, so retention factor, capacity factor, partition coefficient, and what is the value of retention factor, and what is the meaning of that k value. Okay, if k is equal to 0, then what? If k is less than greater than of 20, then what? And k is in between 1 to 20, then what is the meaning that you have understand, and what is the things that will optimize to the to optimize the retention factor. Okay, so separation factor, that is alpha, it is denoted as alpha. Separation factor, that is alpha. So the separation factor or selectivity, it is both are same. So if you also gone through some graph and means in some papers, books and chapters, you will find the separation factor, the term. So at that time you have some idea that what is the meaning of that separation factor. Okay, so separation factor or selectivity is a measure of relative retention, that is K2 by K1 of two sample component as shown in figure. Okay, so in next figure we will show that what is the separation factor. Okay, selectivity or separation factor must be greater than 1 for peak separation. Okay, selectivity is depend on many factors that affect K, means partition coefficient, such as nature of means again the same things, nature of stationary phase, nature of mobile phase, and properties of the solute. Okay, so separation factor is also important term, that is denoted as alpha, and that is called as that is defined by the K2 by K1, and it must be greater than 1. Okay, so in this peak, again now we go by the example. So dear students, if you don't get any understanding from the definitions, so again you will means you have gone through these pictures, I will explain it, and you will get the more idea about this. Okay, so if the compound is if the mixture of sample is having a two component and it having a two peak, that is a one peak at 1.40 and another peak is 1.67 at this figure. Okay, so if I calculate the retention factor, that is retention factor is calculated by TR divided by TR minus TN. So by this way, as we have seen earlier slide, how to calculate the retention factor. So you need to calculate the retention factor of each and every peak, and then you divide the K2 divided by K1. So 3.9, that is a K2, and 3.0, that is K1. And these are the K and K1, and K2 is the retention factor of peak 1 and retention factor of peak 2. Okay, and you need to take a ratio of these two, the 3.9 divided by 3.0. So it has given the 1.3 value. So 1.3 value means it is must be more greater than 1. So it is greater than 1, then and then two peaks are identically separated from the each other. Okay, so it is, you will definitely, now you have some idea about that why it is must be more than 1. If it is less than 1, then two peaks are merged. If the the peaks are merged, then you can call as the separation factor is less than 1. Okay, so after the separation factor or selectivity, okay, we have few more terms like column efficiency and plate numbers. Okay, an efficient column produce sharp peak and can separate many sample components in a relative short time. Means efficient column, what does it mean? Efficient column means a good column. A good column produces a sharp peak and separate many sample component in a relative short time. So many sample component means it has a more capacity. Efficient column means good, and more separate many components, it is called as a good capacity and in relatively short time. So it has a retention factor. So all this comes to a one place. Good column, capacity and retention factor all are come into one place. As seen in most chromatogram, peaks tend to be Gaussian in shape. Again, the meaning of Gaussian, as I already told you, the Gaussian peak means the ideal peak shape. Okay, if you divide the peak in between, the part A and part B both are equal, then it is called as a Gaussian peak. Okay, so it is an ideal peak. As seen in most chromatogram, peaks tend to be Gaussian in shape and broaden with the time, where WB means peak width at base, become wider than the longer TR. TR means retention time. Okay. The number of theoretical plates or plate number n is a measure of efficiency of the column. Okay. So number of theoretical plates or plate number, it is indicate that what is the efficiency of the column. Okay. So that is the n is defined as the square ratio of the retention time divided by the standard deviation of the peak. So how to calculate the plate number? Okay, suppose you take the example the column efficiency with plate number. Suppose in one class of student, one class is considered as a column. Okay, and batches are called as a batch number. Okay, more number of batch, it indicates more number of students can be accommodated. Okay, same like more number of plate numbers, it means more number of compound can be separated. Okay, so likewise here the equation will number of theoretical plates n is equal to t square ratio of TR upon standard deviation. Okay, and it is told that since WB is equal to 4 sigma for a Gaussian peak. Okay, so 4 into 6, so we are removing the 4 over here, we are replacing the value of sigma to 4b, 4WB. So by simplifying this equation, 16 into bracket TR upon WB whole square. Okay, so how to calculate the plate number? Okay, so suppose this is a retention time of 1.67 minute. It is wrongly written here, so pardon this typographical error. It is not a 16.7, it is 1.67. Okay, so again our typical example 1.67. So n is equal to 16 into bracket TR upon WB. So students, if you are writing something, then you can write this example in your paper book, like 16 is equal to 1.67 divided by 0.15 whole square. So it will give 1983 of answer. So it indicates the how much plate number it has. So this is the example of, we have considered the WB, means plate number according to the WB, means it is not as per the USP but as per the other regulatory authorities. While in case of USP, since it is more difficult to measure sigma or standard deviation or WB at a relationship using a width at half height, is often used to calculate N as described in the US pharmacopoeia. So in US pharmacopoeia, it is said that plate number should be derived at the peak width at half height. So whatever we have taken at WB in earlier case here, and for WB at peak weights we have multiplied into 4. But if half height, then we have to multiply it with the 2.355, and it is it is the value given by the pharmacopoeia. There is no means there is no any scientific logic means how they have come up, but it is almost said that if we get half height, that almost 95% of the peak area should be covered. In that sense, they have given one value, that is a 2.355. Okay, and once you come out with this equation, 5.546 into bracket TR upon WB 1 by 2 square. So it is the equation as per the USP. This is the equation as per the other pharmacopoeia, and this is the equation number 10. This is the equation for the other pharmacopoeia, and equation number 11, it is for as per the USP pharmacopoeia. Okay, so whenever you operate the software, in that it is mentioned that USP plate number. Okay, there is a one function, there is a plate number. So in that function, there is a USP plate number function is there. So USP plate number, the software is calculated according to this equation. Okay, so any doubts so far, student? Any doubts?
No, sir, it's good. I think all students getting a very simplified language and
Okay.
understanding. So I think no query, sir. If
Okay.
any student have query, then raise your query in chat box also. We can discuss.
Okay. Okay. So as per USP, this is the equation, and now we are moving towards the peak volume. Okay. Also, a peak volume is the volume of mobile phase or eluate containing the eluating peak. Peak volume is proportional to the retention factor as well as volume of mobile phase. Right. So again, retention factor and means all these terminologies are linked together. It is affecting one parameter which will affect to the another parameter. Okay, so the relationship between peak volume and this factor can be also derived by rearranging these equations. So if I rearranging these equations, okay, so the equation from the equation number 10, if I move the 16 to the denominator of n, and this equation can be rearranged by this, okay, and then multiplying both numerators and denominator by flow rate. Okay, so the final volume of final equation for the peak volume, it is equation number 13, and by the final equation is equation number 14, that 4 into VR upon underscore n is equal to 4 Vm into bracket 1 plus k underscore under root n. Okay, so since for given column and set of operating conditions, n, that is plate number, is approximately constant, n 1 plus k is roughly equal to the k. In most cases, k is much greater than 1. So peak volume is proportional to the k and Vm. So how means if there is a question that why peak volume is proportional to the retention factor and peak volume, then this should be the logic. Okay, then peak height to a theoretical peak equivalent height equivalent to the theoretical plates or plate height. So it is again one questions and one viva questions or one good term in terms of software also, HTTP or H. Okay, so plate number we have defined that N is a plate number, but plate height is also there, so it is denoted as a H or height equivalent to theoretical plate, so it is called as a HTTP. Both are similar terms. So the what is the meaning of that? The height equivalent to theoretical plate or H is equal to the length of the column divided by the plate number. So now column length is generally there is a denoted as a L and plate number is N. Column length is different for the different application purpose. It should start from the 5 centimeter to 25 centimeter. Okay, 5 centimeter, 10 centimeter, 15 centimeter, and 25 centimeter. So column length having a different length, and according to that, plate number is also there. Okay. So HETP, height equivalent to theoretical plate, or H is equal to L upon N. That is equation number 15. In HPLC, the main controlling factor is a particle diameter of the packing. Again, the new term is dp. The dp meaning of the dp is the diameter of the packing. Okay, and again one common value is given for a well packed column. So means for the ideal column, H is roughly equal to 2.5 into dp. So the plate height is roughly equal to 2.5 into dp. So what is the meaning of that? How it is important in our analysis, routine analysis? Suppose in typical 15 centimeter log column, now here one example is taken. The column length is 15 centimeter. Okay, having a column packed with 5 micron material should have N is equal to, means H is equal to L upon N. So we can make a N as a main term, principal term. So N is equal to L upon H. So what is L? L is 15 centimeter. So 15 centimeter is converted into the micrometer. So 15 into 1000, that is called as a mm, and again 1000, then it is called as a micrometer. So 1,50,000 micrometer divided by 2.5 into 5. Why we have converted centimeter into micrometer? Because the particle size we have that is in micrometer. So that's why the centimeter we have converted into the micrometer. Okay. So if you simplify these equations, that 15 centimeter L upon H, so L is 15 centimeter, or we can call it as a 1.50 lakh 150,000 or 1,50,000 micrometer divided by 2.5 into 5. So if you simplify these equations, then it is around 12,000 plates. Okay, it is around 10,000 plates. Okay. So similarly, a typical 15 centimeter column. Now you can just observe these things. Just reducing the particle size only. The same column having the 3 micron material should have a N is equal to L upon H. So it is a 20,000 plates. So just I am reducing 5 micron to 3 micron. Okay, students, we are just giving some more highlights into this term, because based on this, new technique is derived. Okay, so 5 micron is a HPLC, and below 3 micron, the plate number size is increased. So generally, the UPLC, UHPLC, ultra high pressure liquid chromatography have a column size or column pack having a particle size less than the 3, because that's why they have given a more efficient separation in a shorter period of time, because we have increased the plate numbers. Okay, so same column but having just changing in the different particles, 5 micron to 3 micron, we have almost increased the 8,000 plates. Okay, thus column packed with smaller particles are usually more efficient and have a higher plate number. Okay, so what it concludes? If column is packed with smaller particles, are usually more efficient and have a higher plate number. Okay? Then resolution. Okay? So even nowadays, plate particle size is coming with the 1.8 micron or 1.7 micron with the different vendor. Okay, so if you calculate the same column having a 1.7 or 8 micron in size of particle, again the plate height HETP is almost equal to the 40,000 plates. Okay, so we have increased the theoretical, we have increased the plate heights or height equivalent to theoretical plates by just reducing our particle size. And particle size, when we reduce the particle size or column, we are using the column with smaller particles. So it means that we are using the more efficient column because it have a higher plate numbers. Then resolution, that is called as a RS. Okay, so it is also important because whenever you read these books and chapters, then resolution is frequently comes. Okay, the goal of most HPLC analysis is the separation of one or more analyte in the sample from all other component. Okay, so what are doing in HPLC or in any chromatographic technique? Ultimately, what we are doing to separate from each other. Okay, so to separate from each other, and what is the criteria or ideal condition for the separations? It is called as the resolution. Okay, so resolution is denoted as a R, is a measure of degree of separation of two adjacent analytes. Okay, so it is a degree of separation. Resolution, it means degree of separation of two adjacent analytes. RS is defined as the difference in detection time of the two peaks divided by the average peak width. Okay, so by equations, a chromatogram of two peak widths. So, if dear students, if you don't understand by the definitions, then you will get the more information through the equations. Okay, suppose again we are taking the same examples of what we have taken in the retention factor as well as separation factor. Okay, the same examples has been taken for the resolution. If the compound having if the mixture of compound having a two peaks, if the chromatograph is a two peaks, one peak is separated at 1.4 minutes and another peak is separated at 1.67 minutes. So how to calculate resolution? Okay, the resolution TR2, that is a difference between these two. So peak width at base, that is you need to also calculate the what is the peak width at base. Okay, so if 1.67 and 1.4 is there, so if you minus 1.67 minus 1.4, so it will give the delta TR, means 0.27. 1.67 minus 1.40, it means 0.27, and WB1 and WB2, it is measured at the peak width at base. Okay, if it is 0.14 and 0.16 minute, then now you have all the information that will required for the in the equations. So here delta TR, that we have 0.27, and this denominator is 0.14 plus 0.16, it is 0.30 divided by 2 means 0.15, and if you again simplify 0.27 upon 0.15, it will give the 1.8. So resolution is finally achieved by this equation. Okay, so currently software has given the values. Software will give all the values, that what is the resolution, what is the plate number, what is the theoretical plates, what is the telling factor. All these things are given by the software. But how it will calculated at the back on the background, it will you should learn about this. If you don't know this, how it will calculated, or then if any by chance if it is not coming, then you will have a misleading information that you have not getting this resolution, and you maybe try some wrong trials, some non-scientific trials. Okay, so if you know this, what is the effect of peak width, means peak width and the retention time, there are only two factors associated with the resolution. So your more efforts to get the resolutions are on the peak shape and the retention time. Then you will get the resolutions. Right? So this is the equations, and you will get the answer of the resolutions by this equation. Now, what is the meaning of resolutions? Because in retention, like in retention factor, ideal value is 120. In resolution, resolution is ranging from 0.6 to 2.0. So note that if resolution is zero, indicate complete coelutions or no separation. Means there is a no peak separations, or there is a no any coelutions of the peak. So we should avoid that part, that resolution should not be a zero. Okay, resolution of 0.6 indicates that slight partial separations, means points more than 0.5 or more up to 0.6, it indicates it is a slight partial separation. Means peak are generally separated in the, means slightly separated, not fully separated but slightly separated. Resolution 1 indicates that partial separation and is the minimum separation required for the quantitation. So until unless you can't get the resolution 1, you cannot go for the quantitations. You cannot go for the any quantitative analysis with that peak or chromatogram. Okay, so resolution should be at least 1. Okay, and 1.5, it indicates baseline separation. So one peaks are coming, and then it will coming down again to the baseline, and after some time again next peak is coming. So resolution of 1.5 indicates baseline separations, and ideally the goal of most HPLC analysis or methods is to achieve the baseline separation in between 1.5 to 2 for all the key analytes. Okay, so generally when we are planning to do the method development and validation kind of projects in our academic projects or any industry work, the most of the goal of HPLC method having a baseline separations, and a resolution is more than 1.5 to 2, in between 1.5 to 2. So it will have a sufficient resolutions, and it can be it can be considered for the quantification. So this is the chromatogram having a different resolution values. Resolution 0.6, so it means that the two peaks are there, but it cannot be separated. It is a slight separation. Here, resolution of 0.8, it means there is a two peaks, but it is a slight separation. Resolution 1, so you can say that it is a one peak is coming, and it is again reaches to the baseline, and again next peak is coming. So it is called as a means we can consider means that kind of separation at least required for the quantitations. And 1.25, again 1.5, so in 1.5 the peak is completely down to the baseline, and resolution is 2. Okay, so most of the HPLC goal is to getting the resolution 1.5 to 2. So these two conditions we are mostly required in our separation, HPLC separation. Okay, so resolution is must having these. If you will get this kind of separations, you need to update your methods, and then you can do the analysis. Now, peak symmetry, asymmetry factor, and tailing factor. Okay, so again it is also important factor because peak symmetry means what is the peak shape. Okay, and tailing factor, okay, both are equivalent, because we have seen that retention time, flow rate, everything should be ideal, and after that the peak shape, what is the criteria for peak shape. Okay, so under ideal conditions, okay, under ideal conditions means instruments are working fine, everything is, detector is also working fine. So in under ideal conditions, chromatographic peaks should have Gaussian peak shapes with perfect symmetry. In reality, most peaks are not perfectly symmetrical and can be either fronting or tailing. Okay, so under ideal conditions, chromatographic peaks chromatographic peaks should have a Gaussian peak shape. As I said, Gaussian meaning the ideal peak shape with perfect symmetry. In reality, most peaks are not perfectly symmetrical and can be either fronting or tailing. Okay, so in reality, when we are going to actual practical, then it may be a fronting or it may be a tailing. So, what is the symmetrical asymmetry factor? Okay, so asymmetry factor is denoted by AS, is used to measure the degree of peak symmetry and is defined at the peak width at 10% of the peak height. That is called as a 10% means 0.1 in terms of percentage. Okay, note that. Okay, so whenever you have a peak, if you divide from the middle of that, okay, this is middle of that, okay, and whatever you are getting the value, the part A and part B, okay, and that should be divided, and if the value are in positive or in a negative, means below zero and above zero, that will define the peak symmetry or asymmetry. Okay, note that TF, telling factor, is used here instead of T, as in USP T often stands for temperature. So in USP, for telling factor, that is denoted as a TF. Okay, asymmetry factor, as I said, if this part is A and this part is B, so asymmetry factor is B upon A or A upon B. Okay, telling factor is similar term defined by the USP. Okay, so telling equation of telling factor is also same, peak width at 0.05 divided by 2F. So by equations means you will get the basic idea from these. Okay, then I will again go back to the definitions. Okay, tailing factor, if it is greater than 1, okay, then the peak is looks like a this. Okay, so TF1, here the peak shape of TF is equal to 1.2 and here TF is equal to 1.4. So here this part is divided by this is A, this is B. So B divided by A, then you get the information of 1.4. Then you can call, if it is 1.4, then you can call it as a peak tailing. Okay, here also 1.6, the peak shape is again you will get this tailing kind of effect in the peak. Okay, here is a 2, so again peak is sharply started but it is end to the tailing flow, and it is TF4, again it is too much time required to settle down. Okay, and similarly in asymmetry factor, peak is 1 and then sometimes it is fronting start, so in front you will get the slow increase in the peak shape. So when you divide B upon A, so if it is below 1, then it is a fronting. When it is above 1, then it is called as a tailing. So fronting and tailing, two terminology. But in mathematically, when the tailing factor value is below 1, then it is called as a fronting. And when this value is asymmetric factor of asymmetric factor value is below 1, then it is called as a fronting. And when it is above 1, then it is called as a tailing. Okay, so again come to this figure. Tailing factors are required calculation in most cases, most pharmaceutical methods. Okay, TF is equal to 1.0 indicates a perfectly symmetrical peak. So perfectly symmetrical peak means B by A. If you divide your peak into two parts, A and B, okay, and if you divide both part into 1, and if you get one value, then it is called as a perfectly symmetrical peak. T greater than 2 indicates a tailing peak that is typically not acceptable due to difficulty in integrating the peak area precisely. Okay, so T tailing factor greater than 2, it indicates tailing of peak and typically not acceptable. Means when you develop the method and when you go for the analysis, okay, and when you achieve this kind of separations where you find the tailing kind of peak shape, then it is difficult for the integrating, and for that reason the peak area is not considered for the quantitative purpose. Okay, for most peaks, for most peaks, 0.5 in between to 2, the values are most are some kind of, means your aim to be analyze the samples, it is in between 0.4 to 2. The values of asymmetric factor and tailing factor are fairly similar. For severally tailing peaks, AS tends to be somewhat larger than tailing factor. Peak tailing is typically, I mean, what are the reason for peak tailing? Okay, peak tailing is typically caused by adsorption or extra column bed broadening. So for that peak shape, you must have to idea about the rate theory, plate theory, one diameter equations. Those are equations, means uh, the efficiency of the chromatographic separations depends on column efficiency, solvent efficiency. Okay, and the column efficiency, it is based on the rate theory and plate theory, and this is talk about the column bed broadening. So this is all about the rate theory. Okay. Peak fronting is typically caused by column overloading or chemical reaction of the chemical analyte during the chromatography. So if there is any fronting, means that from the starting of peak, if it is something slowly increasing the peak shape, then it is called as a fronting. But it is sometimes it is due to the chemical reaction that has happened when the mobile phase is mixed with the sample. Okay. For instance, many basic analytes or amines display some peak tailing due to the polar interaction with the residual acetic silanol groups in silica based column. So in some kind of group, the peak tailing is hard to remove. Okay, because it is inherent. The chemical reaction is inherent. So whatever the column material it is loaded, that is a silanol groups. It is silica based column. So there is an interaction of basic amine groups of drug or any compound having a basic amine functional group. They can interact with the column, the acidic signal group, and they will give the polar interaction with the polar interaction, and it will convert into the peak tailing. Okay, so for basic, so you can find here, this is one of the USB chromatogram. Okay, it is one of the USB chromatogram. This is a pyridine is very basic in structure, pyridine basic. Okay, so the peak is starting at very sharp, but when peaks come to the end, it shows the some kind of fronting, sorry, tailing. Okay, so it will not have a same shape as he has started. Okay, so it is due to the polar interaction with the acidic silanol group of the column, because pyridine is very basic. So in USP, in some kind of basic amine drugs, the tailing factor is exceptionally accepted to the such a larger values. In suppose in normal drugs, if the tailing factor is accepted at 2, sorry 1.2, but in case of basic amines, some kind of analysis requires the, because in basic compound the tailing factors are generally more, and it is also acceptable from the US pharmacopoeia. So they have given a larger value for the acceptance value for the basic for larger value of the retention tailing factor for the basic drug. Okay, and this is the T-butyl benzene. So it is a perfectly symmetrical shape. Okay, symmetrical shape means Gaussian peak. If you divide your samples from in between, okay, the both parts remains equal. So it is kind of one examples that one basic drug and symmetrical peak shape. Okay, so uracil is very soluble in mobile phase and eluates with the solvent front. So we are just discussing this example. So what is the things happen in the these three combinations? Uracil, it is a very soluble in mobile phase and eluates with the solvent front with K is equal to 0. So it is eluted very fast because it is very soluble in the mobile phase. So it is eluted at very fast and having a retention factor with the zero value. Pyridine is a base and exhibit considerable peak tailing due to secondary hydrophilic interaction with residual silanol groups in C18 bonded phase. Okay, so that's why it shows the tailing because it has a basic and have a strong interaction with the column. And T-butylbenzene is a natural and hydrophobic molecules which elutes much later but with excellent peak symmetry. Okay, so first one is a very soluble, another one is a neutral and hydrophobic molecule, and another one is a middle one is a basic. So by with this we can understand that how it will separate it based on the nature of a compound. Okay, so with this I just say a few words that we have gone through the peak retention. We have started with the basic terminology of ABCD, that retention time, retention adjusted retention time, void of time, retention volume, adjusted retention volume, peak area, peak height, peak width at base, peak width at half height, Gaussian peak, the retention factor, capacity factor, separation factor, or selectivity. Then we have gone through the peak volume, then resolution. In resolution, we have gone through the many terms. Okay, what is the value of resolutions and what are the interpretations? Then we have gone through the peak symmetry. Okay, tailing factor, fronting. So all these are called as a basic terms and concept regarding the HPLC, or we can say for any chromatographic techniques. These are the basic terms and concept. Okay, so whenever now if you understand this terminology and now you go for reading any books of which is uh, based on the chromatographic, then now you will have some easiest way to find to read this book, because you will have some idea about the what is the meaning and what is the importance of these factors. Okay, so dear students, it is almost I have taken 1.3 hours. Okay, 1 means 1.5 hours I have just speaking. There is no response from your side. So if you have any questions, then please ask. I am happy to share with you. I have a very much practical hands-on experience to handle these instruments. So if you find any difficulties to separations, then I can also give some insight on these. Okay. So dear students, if you have a question, then please ask.
See, sir is already described in a very simple language. What are the basic terminology when you use the HPLC? Okay, they always come, and minimum requirement for the development of HPLC, you must understand that what is HPLC. Okay, so I think sir is tell in very simple language. If any student have some query, then ask here. Feel free to ask because sir is very practical. So, and if anybody visit Gujarat Technical University, then also sir help in the show on your laboratory like LCMS, GCMS, because in last week our institute student is already visited, and also
Yes.
happy that sir lab have equipped with the high sophisticated instruments. So thank you, sir.
Yes, yes, we have in our laboratory we have a public testing approval, and having a instrument starting from the pH meter to high-end NMR. We have all the instruments. We have set our portfolio like from unknown to known. Okay, so if you have coming with any unknown molecules, we have all the facility of testing facilities to become a known. So unknown to known, we have all the facilities. So if you have any kind of support that you require while doing this practical work, then you can also approach our laboratory.
So thank you, sir. because almost students have getting inside very brief insight of this topic and
Yes, these are
very
the very basic terms, and might be students are already known, but in a basic concept, it is more important. Uh, so right now, software will give all the values, but how the software background, the calculation is running behind the softwares, that's it is the important part. So I am tried my best to deliver these simple things, but students are very well known to these terms. Then it is also have some more meaningful. So thank you, sir.
okay. Welcome, sir, and thank you on behalf of our SNLPCP team and Vidyabharti Trust for sparing your valuable time and deliver such a nice session, which are very information to student for the future part. Thank you, sir. Thank you,
Thank
sir.
you. Thank you so much.
All participants also can now leave the session. Okay. Tomorrow we will meet.